Okay, great. So yeah, we're going to talk about different kinds of data types today. But before we do that, I just had a question that came in about symbology, and hopefully I can address this here. And I'm just going to use the counties layer for Utah as an example for this one. So right now, this is the symbology for this guy. It's just a single, right? So they're all the counties are looking exactly the same. They're all sort of transparent with kind of a black outline, but turn that off and on, you guys can hopefully see that. And if I want to change that, right now it's single symbol, right? But if I want to make it unique values, for example, I can do that. I can I can choose, right? I can choose what type of actually, let me stop this. I can open up the county attribute table, and I can see, I've got, okay, Kane County, Millard. I can do it by name. I can do it by, state plane, for example. This is an interesting thing. I can do it by county number. I can look at all these different attributes, and I can choose to symbolize the counties based on their different attributes. I'm going to choose to do it on name because, that seems reasonable to me. And so right now, they're all exactly the same. And I could change how that looks. I can double click on this guy and go to properties, and I can change the color of all of them to red, right? That looks awful, but that's what we got. But I can also change it that every county has its own color. And I'm going to do it based on county name, which is probably the same as county number. And so if we look at this, okay, now it's this sort of pastel, Utah. I don't think of Utah as being a lot of pastel colors, but that's all right. Well, let's say I want to alter Emery County. If I just click on it, I can change Emery County, and I can make it yellow, and I can make the outline black, and I can make it a really, really right? So there, Emery County, oh, it's really jumping out at us right now. And so again, that's just, basically clicking on the one that you care about. And then you're able to sort of format each of these guys on an individual basis as you like. So I hope that was helpful. That was, I believe, the question that came up in terms of manipulating individual symbols within a unique symbology situation. Okay, so I'd like to talk a little bit about the data, different types we've got covering today. And again, if there's questions about this or anything else, you guys are more than welcome to chime in or type in the chat. It may take me a little while to see the chat, but today's topic is about different data types. Before we do that, I just actually saw this in the news on BBC News today, this morning, and I thought it was kind of appropriate as we're thinking about your lab 2 and making your maps and making it accessible to people. Wales and Ireland, I'm not a big rugby fan, but Wales and Ireland are going to have a match soon, and these are the colors of their, it's called kit if you're kind of British Isles person. These are their uniforms, right? And one team's color, their traditional color is red, and the other team's traditional color is green. I confess I don't know which is which. If you are red-green colorblind, like the image, the manipulated image in the right is a representation of what you might see if you were watching that rugby game, which would be a terrible experience, right? Because you would just see people wearing what looks like exactly the same color jersey running around, and it'd be very difficult to understand, what's going on. And so, this guy, Jimmy Griffin, he's 23, he's colorblind. He's like super frustrated. Like, why are they doing this? Like, this is, not good. And even though the Welsh and Irish rugby unions I imagine Irish is a green one and Welsh is red, committed to being inclusive. So if they're so committed, like, they should make some adjustments so that their colorblind fans can actually see what's going on and make sense of it. So I just thought that was sort of interesting current news story that is not big news, but it was just sort of interesting. Okay, So where we are, so we are here Friday, February the 4th, talking about different data types. Next week, we're going to get into georeferencing and start lab 3. And next week, again, lab 2 is due. So I hope that that's going well for you guys. And then we've got some other work, and then we get into, President's Day in the middle of the month. Celebrate all of our presidents. Okay, so let's get into some of the content for today, thinking about different data types. And we're going to start thinking about vector data types, vector data models. Again, all types of data in GIS and remote sensing, all of these sort of geospatial technologies, they are abstracted representations of reality. And this is an important thing to remember, right? So like, if you see points in a GIS environment and those points are representing suspect trees that may be infected with the fungal pathogens responsible for rapidohea death, or the points represent, cultural features on Molokai, whatever, right? That's like an abstraction. It's a representation of something that actually exists in the world in all of its variability and all of its, complexity, right? And just to say like, oh, here's a point, right? You've lost a lot of information, right? And so it's just in all of these, they're representations of reality, and they're all flawed representations of reality. There's error in the positional coordinates. There's loss of information. There's all, so just, they're representations, they're attempts at symbolizing reality, and they all fall flat in one way or another. So it's just an important thing to kind of remember. But vector data, they're representing geographic features as points, lines, and polygons. Those are kind of the 3 main guys. And point features represented as coordinate pairs. And again, hopefully this is review for you guys. And then lines and polygon features, they're represented basically as ordered lists of vertices. So points, the simplest thing, 0 dimension, only, infinitely small, it has no area. All it has is this location, right? And so you can think about there's some kind of a geographic, coordinate system here. Down at this corner, it's, the coordinates are 0, 0. And up here it is, 10, 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In this direction, in the X direction, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in the Y direction. So in this corner, it's 0, 0. In this corner, it's 10, 10 in this little example. This point number 1, the coordinates of point number 1, so and it's labeled as 1, so we know that this is 1. So here's a list of the different points: 1, 2, 3, 4, 1, 2, 3, 4, right? The coordinates of this guy are in the X direction 2, in the Y direction 9. So to get to point number 1, which is 2, 9, start at 0, 0, go over to up 9. All right, you guys got this. Okay, so this is this idea of points. And we can work with points from different types of data, right? So lists of data. So this is an Excel spreadsheet that's showing it's actually some point data. It's lead contamination readings from an island in Michigan. And we can see we've got northing and easting. So 2 of the columns in an Excel spreadsheet are the coordinate information, the northing and easting. So you could import this spreadsheet into ArcGIS Pro and display these data as points. Okay, and you guys will be doing that certainly. And again, this is a spreadsheet. In order to put these guys in properly, you have to know some information about these coordinates. Specifically, are they projected coordinates? Are they geographic coordinates? If they are projected coordinates, what type of map projection are we dealing with? In this case, I can tell you it's UTM zone 16 north. But what's the datum? Some other questions are not included in here. But this would be a way to bring these data in and represent them in a GIS environment. So that's a very powerful thing, to be able to take a spreadsheet, to take some kinds of columns of data or something, and then symbolize them, represent them in the GIS environment is a super powerful thing to be able to do. Lines, lines on the other hand, they're just collections of points essentially. So they're arcs. So one-dimensional, they've got location and length. In this case, they're connections of straight line segments. So, and these bold numbers, 11, 12 or such, these are sort of nodes. These are nodes. And then the lighter numbers here, 1, 2, 3, 4, these are the actual line segments. And so line 1, right, it starts at node 11 and ends at node 12. That's the sort of, the first node and then the terminal node. They're also represented by the coordinates of those nodes. So 1, for example, so at 0, 9, so that's where it starts, right? And then it ends at 2, 9. Well, right, easy, right? That's how you can basically represent this line that you see in GIS. Line 4, which is this guy, it's a little bit more complicated, right? It can actually be symbolized as a collection of individual segments, right? And so this guy goes from 8, 9, that's where it starts, to 8, 7, that's where this first guy, right? So that's this first guy, 8, 9 to 8, 7, and then I go 8, 7 to 7, 5, 7, 5 to 6, 2, 6, 2, right? And this is all making up line 4. All right, so that's all, is how this thing is built. It's not very complicated. Polygons, these are, just kind of an additional step up. So now we're moving into two-dimensional. So the big difference is they've got properties of area and perimeter. And so they're a series of connected line segments. So we've got these different polygons in here. Polygon 101, right? So polygon 101 is made up of these different arc segments. Segment 1, segment 4, and then segment 6, right? And you can follow the same kind of idea. And you can count the number of grid cells, right? So 1, 2, 3, or whatever this is. This has a 1, 2, 3, 3 across, 1, 2, 3, 4, 5, 6. So this is 18, 19, 20, and another. It's like 21 square units. That's what we've got for polygon 101. We can also think about these guys as separated from each other by arcs on the left and the right-hand side. So for example, polygon 101 and polygon 103. If we think about this arc segment number 6 right here, and the arrow shows the sort of directionality of this, on the left-hand side of this guy is polygon 103, and on the right-hand side of this guy is polygon 101. All right, so this is how these guys are actually represented kind of under the hood. You don't usually see these individual arcs and things, but you do probably see the attributes, including area is kind of a key one. And, is polygon 101 a lake? Is it a TMK? Is it, property, whatever the property, who owns it, what type of land cover is it? Whatever the polygons are, they may have attributes associated with them that would be more visible in the attribute table. Topology is, looking at the geometry of these different objects in a vector world. This is a map of subway stations in Boston, Massachusetts. So this is how these guys are represented in geographic space, right? So you can see that there's, distances between different stations. For this orange guy, right? The top two, it's not too far away from this station, and then it's a further jump down from this station to this station. Hopefully you guys can see my cursor. This is one way of representing these guys. This is another way of representing these guys. And this is what you might actually see if you go to that subway and you're, I don't know if you guys have had this experience, but you're in a new city, you're on the subway, you're like trying to figure out where you should get off, or if you need to make a transfer or something. Looking at the map on the right is probably easier for your brain to deal with in the stress of, you're being shooken around and, there's people there and trying not to get robbed or whatever it is, versus this one on the left where it's like, things are not all the same distance from each other and such. So, but the topology, the arrangement between, even though this is showing variable distances, the order that the stations comes is exactly the same on the left-hand map and the right-hand map, right? And so that information's been preserved. So there are these properties of these geometric objects, like the order in which the stations come and some other things that is invariant. It doesn't matter how much you stretch this guy, right? But the order of the stations is still going to remain the same. So topology is sort of an interesting area of study. And if you're doing work, particularly using polygons, and you've got, you're making a map for, those counties in Utah, right? You don't have gaps in between those counties. Like, that would be weird. Like, then what does that mean for that sort of sliver of land in between these two counties? Like, who's in charge of that land? So there, the counties can't, and if you can't have two counties that are overlapping, that's also like problematic from a topological perspective. So you can't have gaps, you can't overlap, you can't have any dangles or things like this. The counties have to be closed, and some various things, right? And so these are different things to consider if you guys are creating your own data, you're digitizing polygons or lines or such. Are they connected? Do they overlap, or are they just sort of, a little bit more messy? You want it to be clean if that's what the data is calling for. And this idea about topology is an important one to sort of take into account. Any questions on any of this so far? It's somewhat abstract, but it's not too critical. And again, for topology, this is more background information to have and to think about these arrangements and relationships. It's usually not something that most people, it's at the forefront of their mind when they're looking at a GIS environment. But I wanted to just sort of share that with you guys. All right, if there are, please just let me know. Another sort of vector way of displaying information is use something called a triangular irregular network, or a TIN. And so this is partitioning geographic space into a series of non-overlapping triangles. And oftentimes, if we're using LiDAR data or three-dimensional point clouds, we want to represent a surface. One way to do that is using a triangulated irregular network. And again, it's just, you've got points, and then you basically interpolate surfaces across those different points in the fashion of doing it in a series of triangles. Yeah, it's kind of a very efficient way of generating surfaces. So vector data, it works really great with discrete features with well-defined locations and shapes. Vector data, you can zoom in and zoom in and zoom in and zoom in, and they will never become pixelated or strange looking. They're perfect. They're these perfect abstractions of information. Whereas, and again, they're great for discrete features. So locations of all of the sirens on Hawaii Island, those are discrete features. Vector data don't work as well for spatial phenomenon that vary continuously over space. So topography, precipitation, temperature, these types of things are not typically represented by vector data. Instead, these guys are represented by raster data. Okay, so raster data are basically arrays, or a common way about thinking about these are more kind of like photographs or such. So space is defined or represented as an array of cells arranged in rows and columns. So rows go across, row, 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 and then columns are going up and down, columns, 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 columns. So, and unlike vectors, which store the coordinates explicitly, right? The coordinate of this point is, the X coordinate and the Y coordinate. The raster coordinates for each of these cells doesn't have an explicit, like written into it, XY coordinate. That information is contained in the ordering of the matrix. And I'll talk about that a little bit here. But what you're seeing on the left, is grayscale one, is a continuous elevation raster. And I'm going to show you guys a temperature example of a raster in a little bit here. But The representation of the data values are conveyed to us through the data values themselves, but those are often represented by color. So in this case, the darker shades represent higher elevations, and the brighter shades represent lower elevations. So this bright area is probably some kind of a valley or something like this, and then this darker area up here is likely a hilltop. Okay, so it's the colors are telling you something about the properties of the data set. In this case, the colors are representing elevation. In this example on the right, the colors are representing land cover type. Okay, so blue, all these guys which are blue, that's representing that it's lake. The green is agriculture, the yellow is road, and then the red is residential. If you're red-green colorblind, this will be a little bit challenging for you. Right, so the colors tell you something about the underlying data set and what they are. This is a representation of some data that I collected a few years ago up in Upper Peninsula, Michigan, actually an island, Isle Royale National Park, a small island called Passage Island, which is, there's a lighthouse there, and because it's old and they used to use lead paint, it's caused a bunch of lead contamination in the soils in this area, and there's some endemic amphibians there that don't like being contaminated by lead, and so one of the things that we were asked to do is go there and make a map of soil contamination. I'm not showing you the soil contamination data right here, but I am showing you a representation of elevation in this area. So what you're looking at here is, well, this inset in the right is the laser scanner we use to kind of generate these data, but the colors that you're seeing are representing elevation, right? Just like before it was black and white. This is colored, right? So the redder colors are higher elevation, and then the greens are the lower elevation. And then it's water out here. And this is the area that we scanned. And this is being depicted not only with color, but also to sort of help these landscape features jump out at you. I've put in a hillshade model. And a hillshade model is a product that you can generate derived from elevation data, which basically simulates what that landscape would look like if the sun was shining on it. And oftentimes a good way to represent sort of geomorphic areas and elevation change. Oh, right on. Julia is from Northern Michigan. Yeah, so this is Passage Island on Isle Royale. Isle Royale. I don't know if you've ever been up there, but it's amazing. Isle Royale it's famous for a study looking at predator-prey dynamics, looking at sort of moose and wolf populations over more than 50 years. Super interesting place, gorgeous, but a lot of black flies and they'll eat you alive. Anyway, again, representing this landscape and looking at differences in elevation using color to do that. In the example I'm going to share with you guys, you can represent these rasters with different color schemes to bring things out, but that doesn't change the underlying data. You can make them look totally different, like you make it black and white. You can make it, grayscale. You can make it colors. You can, change how the colors are shown. Those are all representations of how it looks. They're not changing the data themselves, and that's an important point to make that not everybody gets. Raster data can also represent things like, numbers of points in an area, right? So let's say you've got a grid, and then you've got some kind of point data. Let's say that these points are representing a particular kind of invasive plant, right? And somebody went out there and they, marked out the coordinates of these invasive plants. So in this cell up here, you've got 1. In this cell over here next to it, you've got 3, and then 0, 0, and then a 1, and then maybe a 12 or an 8 or such. So we start out with a grid. We have our point data on the grid. We count them up. That's what's shown down here, and then we can visualize those with colors. And so the one which is 12 is represented by the darkest color. The zeros are the lightest color. Down here in this lower corner, this is a 10, right? And so this is a way to kind of represent these point data in a raster format, right? So again, you're doing some artificial stuff, right? You're breaking the landscape into, these maybe somewhat arbitrarily sized grids, and then you're saying, what's the count? So this is like a point point density raster that we've generated. So rasters can depict elevation. They can depict all kinds of different things. And there's benefits and drawbacks to all of these different guys. One of the things is, again, this idea about rasters have a set resolution. Okay, so on the right you've got these vector guys. You got points, you got lines, you got polygons, and on the left is a raster representation of those guys. So even though this point may be infinitely small, in a raster environment, it'll be shown as, it'll fill up the whole grid cell where that point occurs. Same thing for lines, right? It'll fill up these grid cells for where these lines are generated. Same thing for polygons, right? And so depending on the resolution of the raster, things may get kind of blocky looking, right? So the polygons that we're seeing here, they've got these shapes and whatever else, and those are now sort of more abstractly and blockily represented in the raster. But there's a time and a place for raster and vector data. I teach classes in remote sensing, at least one main class here at UH Hilo. I think we're trying to work up to a sequence, and we think about things like hyperspectral remote sensing, where instead of a single raster, we've got hundreds and hundreds and hundreds of rasters all stacked up on top of each other, each of them representing a different part of the electromagnetic spectrum. And from those, we can generate things like this blue line here, kind of spectral profiles that can tell us about the properties of things. But they're all really at their heart just a sequence of these rasters, right? A sequence of individual rasters that are associated with spatial information, and then whatever the value is. In this case, it's going to be like reflectance value or such. How much light is bouncing off that surface? Raster data, again, hopefully can be georeferenced, and basically the columns corresponding to the x coordinates, so in an east-west direction, and then the rows corresponding to y coordinates in a north-south direction. Usually the origins in the upper left. And if we know information about these guys, sorry, I kind of jumped pretty quick through there. So the origin of the raster is in the upper left. Sometimes it can be in the lower left or such, but for this purpose, we're going to say the origins in the upper left. And it depends on your projection, right? Your coordinate system. So in this example, we're using universal transverse Mercator. So UTM coordinates. And let's say we've got a raster, it's got 463 rows, right? So 463 of these guys going across. What I'm showing is just a portion of this. And then 318 columns. So 318 columns, 318 columns, blah, blah, blah. And the cell size in this example is 30 meters. So that means each of these pixels is 30 meters by 30 meters, 30 meters on a side. And the lower left coordinate in this UTM example here is going to be 4,99995 and then 5,177,175. And then the upper right corner is going to have these coordinates. Okay, this is just sort of an example, right? So this information is held in the metadata for the raster. And you can verify that by looking at the difference in rows, dividing by 30, because each of these guys is 30 meters across. And you end up with, 463 rows. Well, I told you there are 463 rows. So the math sort of backs this up by saying the number of rows, and that's basically counting the row value at the top minus the row value at the bottom. So these numbers are signifying the rows, right? The row values, and these numbers are signifying the column values, right? So the number of columns, it's this number minus this number minus this number. Because each of these cells is 30 meters across, we divide that by 30 and we get 313 columns. And that is indeed the case here. If this is not making perfect sense to you, it's okay. But we can glean information about the rasters based on their size and their geometry, but we need to know something about the map projection or the coordinate system that raster was generated in. We can also figure out the coordinates of each cell. Basically, if we know the size of the cell, you just do some math, and then halfway through, that's what the coordinate of the middle point is going to be. Rasters are great, again, for representing, continuously changing properties across space. So USGS topographic maps, these are rasters. This is a representation of a raster from Mars, right? Showing topography. If you take a photo, this is an oblique photo of the UH Hilo campus, that photo is a raster, right? And that's actually, you could, regardless of what the photo is, you can think about that as a scientific measurement of whatever it is that the photo is of. And if it's an oblique one, there's an interesting thing where, pixels at the bottom edge of this guy are representing, all the pixels in this photo are the same size, but because it was taken at an oblique perspective, the pixels along the bottom are covering a smaller area than the pixels at the top, right? Because you got this perspective thing going on. And then this rainfall atlas of Hawaii, this is another way of depicting this idea of this continuously varying information. And so I want to do a kind of an example with some data that my group collected for the Hawaii County Fire Department, focusing on a bagasse fire, which unfortunately is ongoing, burning down in Ka'u. And if you haven't heard of bagasse before, it's a funny word, but it basically means the dry fibrous residue remaining after you extract the juice from crushed stalks of sugarcane. Now, there's not a lot of active sugarcane production going on currently. There's a little bit up in Hawaii area for a rum company, but there used to be a lot. Sugarcane was sort of the dominant agricultural sector on Hawaii Island, and major employment, big efforts going on, and as such there are big piles of sugarcane bagasse that are sort of remnant on our island. And it's unfortunately, it can catch on fire. And that's what's happened down in Ka'u in the Honuapo area. And unfortunately, it's actually injured a number of people. They've gotten burned. So the fire count, so my lab does some work, and we're able to use drones with thermal cameras and such. And so we're able to actually image these areas. And I wanted to share with you guys an example to think about this information about raster areas and vector and these kinds of data. So this area of interest is down here. This is the location. So it just looks like kind of a landscape, but the truth is all of this is covered up by this bagasse. And this yellow guy, this is what kind of data is this? This yellow guy, this is a polygon. All right, so this is vector data. And so and underneath here, we've just got kind of a base image. But if I zoom in on this vector, it's not becoming pixelated, right? It's always staying a perfect line, right? It's always staying a perfect line. So again, it's a polygon. It's this sort of polygon. This is the area that we were interested in covering and mapping for the county. And we did that using a camera, which is a thermal camera, sensitive to temperature. And we ended up with areas that we focused on that had these burning fires. So that's what's shown here. And this is a raster. So if I zoom in on this guy, right, you can start to see it getting kind of pixelated, right? And if I want to know the size of one of these pixels, right, that tells me the resolution of the image. And I can know that a couple different ways. I can measure it, right? I can measure the distance. So I can say, okay, from here to here, what is that? That's about 14 centimeters or so, right? So I can right click on this guy, and I can go to properties, and I can go to source and raster information. And that'll tell me the cell size in the X and the Y directions, right? And this is in meters, so this is 0.14. So that's 14 centimeters in the X direction and 14, 164, blah, 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 in the Y direction. Essentially, 14 centimeters across each of these pixels, right? And I can know that again, right click in the properties and it'll tell me stuff about this guy. The pixel values here represent temperature. So if I click somewhere in here where I just clicked, I don't know if you guys can see this, but let me turn off mapped area. If I up here, it's going to tell me that this is not a direct measure of temperature, but it's like a relative, right? So in this yellow here, it's like 30, 34. Again, I don't know hopefully you guys can see that. It's pretty tiny numbers. So 34, if I click out here, this is now 17. If I zoom out and I click somewhere over here in this sort of, blue area over here, this is 12, right? If I click again in the yellow, this is 37. I click in the purple, this is 15. Now, and these yellow guys are places where there's fires burning, these underground fires burning. Now, maybe I don't like this color scheme, right? Maybe I'm like, I don't really care for this. I want to show it a different way. And I want to represent it for some reason. I want to represent it with this. Okay. All I've done is I've changed the colors of how the thing looks. I haven't changed the underlying data, right? If I click here and I turn this guy off, this is saying 47. It's 47 whether or not it's blue yellow or whether or not it's purple yellow, right? That doesn't really matter. How it's being shown, the visualization of it doesn't matter. It's really more about the underlying data, and you can change these ways of depicting it. So this is with standard deviations. I can say there's no stretch. I can say I want a minimum maximum stretch, right? I can say I want a % clip stretch. I can say I want, all this is doing is sort of, refining how the data are looking in a way that allows you the features you care about to kind of jump out. So we took this information and we did some work with the raster itself to basically only highlight those things that we thought were fires. Right. So we've got this guy, and then we've got this purple one on top is still a raster representation, right? Because if I zoom in, it's like kind of blocky like this, right? But then from that, we went ahead and we got a vector of this guy. And that's what's shown by this red one. Again, I can zoom in, and it's perfect, right? It's never going to get more and more pixelated. It's always going to maintain these types of clean vector lines. And then from here, you can, do some things like open up the attribute table, and you can figure out the area of these different shapes and, the collective information about this. And you can be more or less conservative, right? This was a fairly conservative one. Presumably the fire area is a little bit bigger than what we're seeing here. But this is a useful way of, again, getting at areas for these ones by converting it to a vector. Because then you can say, what percentage of this area is, burning, and what percentage, what's the area? Whereas from the raster, just the straight up raster, this is just pixel information, right? You got to do something to this to get at these calculations and areas and different differences. And actually, my group is going to be heading back out here, I think next week if all goes well, to refly this. This is from a few years ago. No, this is from September of 2021. This is maybe 6 months ago, to see how things have changed. So that is what I wanted to share with you guys about different data types. I hope that was somewhat interesting. Again, we got vectors and rasters and all this good stuff. And yeah, so I'm going to go ahead and stop recording, and then I'll